on to polynomial functions of degree 3, section 5.2. In 5.1 we did polynomial functions of degree 0, degree 1, and degree 2, so that was all review. Now we're doing some new stuff, which is degree 3. Polynomials of degree 3 are called cubic functions, and basically what we're going to do here is we're going to graph 6 cubic functions, and then we're going to look at the properties of them and summarize, and we're done. Shouldn't take too long. So for the first one, y equals x cubed, guess what this is? This is the mother function. This is the most basic cubic function here. So we don't know what it looks like, right? So what can you always do when you don't know what something looks like and you're graphing? You can always do a table of values. Don't worry, we're not going to do table of values for all these, but we will for the first one or two. So again, we're going to, x is our input. We can pick some nice inputs. Why don't we use what we've used a lot in this course, 3, 2, 1, 0, negative 1, negative 2, negative 3. That way we get some positive, some negative, and 0. So you just put 3 in here, 3 cubed. That's 3 times 3 times 3, 27. 2 cubed, 2 times 2 times 2 is 8. 1 cubed, 1. 0 cubed, that's 0 times 0 times 0, 0. Negative 1 cubed, so negative 1 times negative 1, which is positive 1, times negative 1, which is negative 1. 3 negatives make a negative. Negative 2 cubed, negative 8, negative 3 cubed, negative 27. So you can see cubic functions go up fast. 327 doesn't even come close to fitting on this graph. 2, 8 just fits on the graph. 1, 1 fits, 0, 0 fits, negative 1, and negative 2, negative 8. And so what you get is something that looks like this. Keeps going up here and keeps going down there. Something like that. Okay, that is the mother function for cubic functions. Now, if you did this one here, y equals negative x cubed, say you were going to put the 3 in here. Does that mean it's negative 3 cubed? No, it means 3 cubed, which we already did, it's 27, and then negative, so it's negative 27. If you put 2 in there, you get 2 cubed, which is 8, and then put a negative. So the only thing that's going to be different is all the values are going to be negative. Negative 27, negative 8, negative 1, negative 0, well that's still 0. Now, this is negative, negative 1, right? Let's try this out. If I put negative 1 in here, I have y equals negative, that's that negative. Then the x value is negative 1 cubed. So I go negative 1 cubed, which is negative 1, and then I have another negative. So negative, negative 1 is positive 1. So this is positive 1, this is going to be positive 8, this is going to be positive 27. If you graph those, 3 negative 27 doesn't fit, 2 negative 8, 1 negative 1, 0, 0, negative 1, 1, negative 2, 8, and there you go. If you compare this graph to the previous graph, how do they relate? They're mirror images of each other. This is the effect of putting this negative value up front here. It reflects the graph over the y-axis. So just, my graphs are okay, but if you want to see beautiful graphs, go to Desmos. I've already got them all set up here. Y equals x cubed, that's the first one I drew. Okay, there it is. If you want, you can see more of it. I'll make it smaller, and it just keeps going up and up and up and up. Okay, and y equals negative x cubed. There it is. There's your mirror image. Hey, it kind of makes it look like you have 2 parabolas, but you don't. You have 2 cubic functions here. So now what we're going to do is we're going to graph some of the other ones on this page, but rather than using table values, we're going to use Desmos because I do not want to have to plug numbers into all this. So here we go. The first one is y equals 2x cubed minus 15x squared plus 33x minus 20, and if I turn that one on, there's what it looks like. Okay, interesting. So a couple things. It goes through 1, it goes through 4, and it goes through 2.5. Those are the zeros in this case, right? The x-intercepts are at 1, 2.5, and 4. So let's go put those in first. 1, 2.5, and 4. Now, for today's work, I don't care if you get the graphs exact. I just want you to get a general sense of the shape of these things. So again, if I go back here, you can see that between 1 and 2.5, it's above the x-axis, then it comes down below the x-axis, and then it goes way up. And same on this side of 1, it just keeps going down, down, down. Something that's interesting here is, what's the y-intercept? Can you tell what it is? The y-intercept is right here. The y-intercept is negative 20. Negative 20, interesting. Maybe I'll just write that down when we go back to our other page. So remember what this looks like, and let's go back here and give a sense. We can't put the negative 20. Remember I'll just write it down here. Y-intercept equals negative 20. And what happened with this graph is it came up, it went up here a little bit, it came down here a little bit, and then it went up like this. Okay, that's not perfect, but that gives you an idea of what this graph looks like. It's not broken there. There you go. It goes forever down there, forever up there. We're finished. Okay, nice. Let's look at the next one. Turn this one off. Y equals negative 4x cubed plus 16x squared minus 16x. So we'll turn that one on, and there it is. So a couple of things again. Let's look at the zeros. There's a 0 at 0, and there's a 0 at 2, and that's actually a point where the graph turns back around, isn't it? So 0 and 2, and the y-intercept is at, obviously, 0. That's where it goes through both the x-intercept and the y-intercept there. So let's go back here and put 0 and 2 for the x-intercepts. So what happened this time is the graph came from way up here, came down, I think it went down to about negative 4, maybe a little lower, came up to the 2, and it kind of bounced off there and went down like this. There's the general sense of that one. So the next one, if you compare this equation that we just graphed with the next equation, do you see they're exactly the same? Negative 4x cubed plus 16x squared minus 16x minus 6. Minus 6. Let's see what happens if you have minus 6 in there. So I'll keep that first one, and then I'll put the new one on there. The yellow one's the new one we just added. You can see the shape is identical. It just looks like the whole thing's been shifted down. Now, how much has it been shifted down? The y-intercept of the purple curve is at 0. The y-intercept of this yellow curve is at negative 6. It shifted the whole thing down 6 steps. Oh boy, I think I see what this negative 6 is. So y-intercept at negative 6. There's only one 0 or one x-intercept. It's just below, what is that, negative 0.2 or something? So let's see if we can give a general sense of this one. So we said the y-intercept was at negative 6. We said the only 0 was somewhere around here. I know I probably haven't drawn that too well, but you get the idea. And it had the same shape as the last one. So it started from way up here. It came down through here. Comes down a little way, probably all the way around to about negative 10. And then it came up, bounced off some point, and came down. It's supposed to look exactly the same as the last one, just moved down 6 steps. I know, that's pretty bad, but I'm not going for accuracy here. Alright, the last one, we'll turn these two off, because this last one doesn't look the same as those ones. 2x cubed plus 10x squared plus 6x minus 5. And if you take a look at that one, it looks like a parabola at first, but I think if we continue, there we go. There's a better sense. Maybe I can make it a little smaller so it fits. Yes, so we have the y-intercept is at negative 5. We have 3 zeros. One's between negative 4 and negative 5, one's between negative 1 and negative 2, and one's between 0 and 1. Okay, and the y-intercept at negative 5. Can I remember all that? I don't think so. I think I've already forgotten. So the y-intercept was at negative 5. We said we had 1 0 between negative 4 and negative 5. We said we had another 0 between negative 1 and negative 2. And we said the last 0 was between 0 and 1. Now let's go back and get a general sense of the shape. So it comes down, goes through the y-intercept, goes down a little bit more, and then goes quite a ways up and down. Alright, let's try. Alright, it comes down from here, goes through the y-intercept, goes a little bit lower, then it comes up here. I think it actually goes up to above 10. I'm just going to draw it up to about there, and then it comes back down again and goes through that one. I'm so embarrassed by these graphs. But it's hard, I tell you. It's hard to draw these things. So there you go. That's what that one basically looks like. Okay, now the most important part. Well, we're going to define some terms first, then we're going to go through the generalizing all the graphs, things that stay the same, things that change, all that kind of stuff. So a turning point. In their book they call these turning points, and what a turning point is a a point where the graph changes from increasing to decreasing, or vice versa. So it might change from increasing to decreasing, or decreasing to increasing. So if you look at these graphs here, do you see where the turning points are? Well, you have a turning point right here, because the graph is decreasing, 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 whoa, increasing, 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 whoa, there's another turning point there, decreasing, decreasing. Those are turning points. This is a turning point. This is a turning point here. I prefer another name I've read in other books. It's called local maximum and local minimum. So this is a local minimum, right? Because it's going down, 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 and now it starts coming up. That's a local minimum. And this is a local maximum because it's going up, 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 maximum, and that comes down. Why is it called a local maximum and minimum? Because it's not truly the minimum. This point here is not truly the minimum. Why is it not truly the minimum? Because in this graph, there is no minimum. It keeps going lower and lower and lower. If you want a minimum, it's negative infinity. Why is this not the just called a maximum? Because it's not the maximum. The maximum in this one's positive infinity. It keeps going forever and ever and ever. So I kind of prefer those terms, local maximum and local minimum, but your book just calls them turning points. Here's one turning point, here's another turning point. So if you go back to the other ones, let's look for more turning points. Oh, got to use a different color now. Here's a turning point here, and here's a turning point here, and in this graph over here, here's a turning point, and here's a turning point. And then if we go up here, where's a turning point? Is this a turning point? Well, not really, because it's decreasing, 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 still decreasing, decreasing, decreasing. Is this a turning point? No, still decreasing, decreasing. Is this a turning point? No, still decreasing. So there's not really a turning point here. But what we do have is an inflection point. And what an inflection point is, it's the point where the curvature of the graph changes, but the graph does not change direction. So if we go back here, where we actually consider the inflection point is right here. This is the point where it changes direction. And in this graph right here, this is the inflection point right there. Okay, with all that done, let's take a look at these things. The domain and the range of these graphs. If you look at all the graphs, we'll just look at these two, but the other ones are the same. Let's look at the domain. This gets wider and wider and wider and wider as it goes up. And this goes further and further and further to the right. Same with this one. Comes out and out and out and out further to the left. I mean, it's not going out to the left very fast, but it is moving out to the left. And this one's also moving out to the right. Not very fast, but it's going forever. So it's eventually going to get as far as you want out there. In other words, the domain is x is an element of all real numbers, or negative infinity to infinity. How about the range? Well, that's even more obvious. This goes straight up practically. It's going way up to infinity. This one's going way down to negative infinity, and they're both doing that pretty fast. So this is y is an element of all real numbers from negative infinity to infinity. And this will always be the same for cubics. Let's actually go to y-intercepts here. And we can't say what the y-intercept is. Well, we kind of can. How many y-intercepts are there? Well, in this question here, there's one y-intercept at -5 was our y-intercept. In this one, we had one y-intercept at -6. At this question here, we had the y-intercept was at 0. You really could have +0 there, couldn't you? -20, and yes, we said the y-intercept was at -20 here. 0, and again, you could put +0 here. 0, and you could put +0. So two things. How many y-intercepts are there? In all these cases, and forever with cubic ones, there's only going to be one y-intercept. So you're going to have one, I'll put always 1 at d. Why d? Because what we're looking at here is cubic functions of the form y equals ax cubed plus bx squared plus cx plus d. And that d value right there, that's the constant term. And that constant term will tell you what the y-intercept is. Okay, x-intercept. Let's take a look at how many x-intercepts we have in this case, in all these cases. So in this one here, we have 1, 2, 3 x-intercepts. And this one we have 1, just 1. Different, okay. 3, 1, how many here? Just 1. How many here? Just 1. So, how many here? We have 1, 2. And how many here? 1, 2, 3. So it looks like we could have 1, 2, or 3 x-intercepts. You're probably thinking, well, what about 0? Can you have 0? And the answer is no. It's a fact that for cubic functions, the number of x-intercepts will always be 1, 2, or 3. And we'll explain why there can't be 0 when we get to end behavior here. Okay, turning points. How many turning points are there? So I think I've already drawn the turning points. In this one here, there was a turning point and a turning point, so that's 2 turning points. We have a turning point up here and a turning point down here. That's 2 turning points. Down here we had 1, 2 turning points. Here we had 1, 2 turning points. Are they all 2? Nope. How many turning points are here? None. No turning point. No turning point. We just have those inflection points there. So it works out that the possibilities for turning points is there will always be, sorry I'm not using red, 0 or 2 turning points. And the end behavior. Okay, with this one, it's going from quadrant 2 to quadrant, this is 4 down here. This one's going from 3 to 1. This one at the top here is going from 3 to 1. This one, when it was reflected, went from 2 to 4. This one goes from, okay, where does this one end up? It looks like right now it's from 4 to 1, but is it? No, remember there's a y-intercept at -20, and then once it crosses over -20, it's going over to the other quadrant. So again, this one is from 3 down here and 3, and it goes to 1. And this one is from 2 to 4. So it looks like there's only 2 options here. It's either 3 to 1 or 2 to 4. Okay, what does that remind you of? Which other of the functions that we've done so far is that the same as? Is it the same as polynomial functions of degree 0, 1, or 2? It's the same as polynomial functions of degree 1. Linear functions. Linear functions either go with a positive slope from 3 to 1, or if they have a negative slope, they go from 4 to 2, 2 to 4. So this is the same as linear functions. They'll always either go from 3 to 1, and by the way, that'll happen if the a value is positive, and it'll go from 2 to 4 if the a value is negative. Let's make sure that's true. If we look at this one, it went from 3 to 1, and look at the a value was 2. It's a positive 2. It goes from 3 to 1. This is a negative, so it goes from 4 to 2. This is a positive. There's a positive 1 right there, so it goes from 3 to 1. This is a negative, negative 1, so it goes from 2 to 4. This is a positive 2, so it goes from 3 to 1, and this is a negative 4. It goes from 2 to 4. So that takes us back to this question: why can't there be 0 x-intercepts? Because if you're starting down here and you need to get up here, is there any way from go to here without crossing this? No. If you're going to make it continuous, which all polynomial functions are, it has to cross somewhere. Same if you're starting here and getting here. The only way you're getting from here to here is if it has to cross here somewhere, and this is why you can never have 0 x-intercepts.